Hello everyone, welcome back to MES Videos. If you've got a question, we've got a solution. On today's episode, we are going to discuss on something that many of us would love to have in our car's engine. Turbocharged engines are quite common today in the car and heavy vehicle market. All the diesel engines and many petrol engines too today come turbocharged. But let's find out what could have led to introducing these into the common market. A basic engine that has no additional resistance for air intake is called a naturally aspirated engine. If you have seen our earlier videos, then this is quite familiar. Hence, if you wanted more power, then you needed to go for bigger engines, like in the case of bigger SUVs or higher performance or sports vehicles. But then, bigger engines incurred higher cost, both for production due to its size and for usage because of the more fuel it consumes. Also, burning more fuel in turn releases more emissions into the atmosphere. So what was the alternative solution? If I needed more power, I want it at a lower cost, I don't want to pay too much for the fuel, and I love my planet. The only way possible was to maintain the power output and reduce the overall size as smaller engines consume less fuel and is lighter by weight. In the year 1878, a Scottish engineer, Douglas Clark, made a successful attempt of supercharging a two-stroke engine. A supercharger forces more air into the engine and hence you get a stronger boost of power. A supercharged engine has a blower connected to the engine, and as the engine speed increases, the blower speed also increases, and hence more air is forced or charged into the engine, thus boosting the power of the engine. But isn't a small part of the engine's power being consumed for supercharging the engine? Then how can we prevent this loss of power and utilize it completely for running the vehicle? In the year 1905, a Swiss engineer, Alfred Buchy, found an alternative to supercharging by utilizing the force from the exhaust instead of directly using a part of the engine's power. This is called the turbocharger or the turbo. A turbocharger is made of two sections, a turbine section coupled by a shaft to a compressor section. The turbine is used to spin or drive the compressor with the force from the exhaust gases flowing out of the engine. This spools or spins the compressor, which pulls in the fresh air from the atmosphere and forces it into the engine at a higher pressure, which is also called boosting. The illustration shows the exact working process of a turbocharged engine. The air that is taken into the compressor from the atmosphere is compressed, which rises the temperature of the air and needs to be cooled to a lower temperature before charging it into the engine for maximizing the working efficiency. But then still the boost happens only at a much higher engine speeds. What about till then? Now, how can I get that boost at a lower engine speed, or in simple terms, reduce the lag? The solution initially was to introduce a turbocharger that starts off boosting at a much lower engine speed range. But then, at higher engine speeds, the boost would be too high to be handled and should be controlled. A valve called the wastegate was introduced to optimize the flow of exhaust gases into the turbine and made it easier to modulate the turbine speeds, hence reducing the lag and maintaining the boost for a wider speed range. In the year 1953, Garrett introduced the variable geometric turbocharger that worked on the principle of adjusting the effective size of the turbine, or in other words, the aspect ratio of the turbine. The wastegate was replaced by vanes in the turbine section that can tilt its angle according to the requirement. Initially it was done mechanically, but modern VGT has an electronic boost control module to achieve this with a higher precision. Hence, there is almost no lag and the boost was available for a wider engine speed range too. So that brings us to some great achievements. The engine could be compressed down to almost 75% of the size of its naturally aspirated counterpart for the same power output, and a massive improvement in the power and the torque outputs from the added boost has increased the performance by around 40% over its equisized naturally aspirated engine. And more air being charged into the engine helps achieve a cleaner combustion as well. Of course, it does consume more fuel as more air is being charged into the engine. But in reality, it consumes just a bit more fuel than its equisized naturally aspirated counterpart only. Modern applications are numerous and more demanding, especially when it comes to higher performance sports applications or heavier and larger applications as well. Therefore, we have multiple turbochargers lined up in different layouts to get the desired results. Let's have a quick glance on how more number of turbochargers are put together. Here is a twin turbo setup in a sequential layout. Here, one turbo is used to boost air into another, which further boosts the charge. This layout is done to reduce the lag and enhance the boosting range. The first stage works during the lower engine speeds, and as the engine speed increases and more boost is needed, the second stage provides the additional boost. A twin turbo in a parallel layout is used for engines of a larger capacity. In this layout, there are two turbos charging in at the same time, and hence there is more volume of charge coming in. Here, the priority is to provide a stronger boost, unlike the previous one which focused on a wider range to boost. In the case of extreme performance or to extract more out of a large capacity engine, you need more number of turbos getting into the picture. This layout is made of two sequential layouts acting in parallel. This layout is more often seen in higher-end sports cars to cater to the prolonged boost that has to be provided to the large capacity engine for a very long range of working speeds. And now when we look into the layout where you have 4 turbos charging in parallel, then you are looking into a huge engine where the demand is more charge and to provide an extremely strong boost instead of a wider working range. In short, if you are looking for a stronger boost, you need more charge, and hence the parallel layout will be better preferred. On the other hand, if you need a longer range of boost, then the sequential layout will be the better way to go. Finally, the exhaust gas recirculation unit will complete today's discussion. A very small portion of the exhaust gas is recirculated into the engine. This is done to help slightly lower the combustion temperature inside the engine cylinder, reduce the nitrox pollution, and improve fuel economy. When a small portion of the exhaust gas is recirculated into the engine, it displaces a bit of the fresh charge that was to be taken in, and hence correspondingly the fuel intake is lowered as well. This reduces the combustion temperature and reduces the excess oxygen available for nitrogen to oxidize. Well, I hope that mess was sorted out. We hope you enjoyed this episode. Please hit the like and subscribe button and stay tuned for more mess.